Chapter 12.4, the normal distribution. Suppose that a researcher selects a random sample of 100 adult men, measures their heights, and constructs a histogram for the data. That graph is illustrated below, right here, along with the illustration of what happens as the sample size increases. Right? So here's a sample of more men and even more men. If you were told to fold the graph down the middle, the left side would fit the right side. Such a histogram is called symmetric. As the sample size increases, so does the graph's symmetry. If it were possible to measure the heights of all adult males, the entire population, the histogram would approach what is called a normal distribution. This distribution is also called a bell curve, or the Gaussian distribution, which is named after the German mathematician Carl Friedrich Gauss. The normal distribution is bell-shaped, there's the bell shape, and symmetric about a vertical line through its center. Furthermore, this means that the mean, the median, and mode of a normal distribution are all equal and located in the center of the distribution. Okay, think about what it means to be the mode. Okay, it would be the highest point on our graph, so this is obviously the mode. The mean is the average, and if your distribution is symmetric, then that falls right in the middle. It's kind of the balance point, if you will. And then the median is the value exactly in the middle, which again, if you're symmetric, that value that's in the middle would be exactly in the middle. So that means the mean, median, and mode of a normal distribution are all equal and located in the center of the distribution. So from now on, as soon as I hear that a distribution is normally distributed, I'm immediately going to draw this bell curve shape, right? And then we're going to add some information to that. So the shape of a normal distribution depends on the mean and the standard deviation. Notice these are all bell-shaped, but some of them are wider bells than others. Below, we see three normal distributions with the same mean, but with different standard deviations. As the standard deviation increases, the distribution becomes more dispersed or spread out, but retains its symmetric bell shape. The normal distribution provides a wonderful model for all kinds of phenomena because many sets of data items closely resemble this population distribution. Examples include heights and weights of adult males or females or babies, intelligence quotients, SAT scores, prices paid for a new car, lifespans of light bulbs, many populations. In these distributions, the data items tend to cluster around the mean. The more an item differs from the mean, the less likely it is to occur. The normal distribution is used to make predictions about an entire population using data from a sample. In this section, we focus on the characteristics and applications of the normal distribution. Okay, the standard deviation plays a crucial role in the normal distribution, and it's summarized by the 68-95-99.7 rule. Okay, it tells us that approximately 68% of the data items fall within one standard deviation of the mean. Now this means in both directions, right? Both directions. So right here, here's the mean and the median and the mode, right? The mean right in the middle, and within one standard deviation of that mean in both directions is 68% of the data. Approximately 95% of the data falls within 2 standard deviations of the mean, right? 95% of the data. And 99.7% of the data fall within 3 standard deviations of the mean. A very small percentage of the data in a normal distribution lies more than 3 standard deviations above or below the mean. As we move from the mean, the curve falls rapidly and then more and more gradually toward the horizontal axis. The tails of the curve approach but never touch the horizontal axis, although they are quite close to the axis at 3 standard deviations from the mean. The range of the normal distribution is infinite. No matter how far out from the mean we move, there is always the probability, although very small, of a data item occurring even farther out. So now that I know this 68, 95, 99.7 rule, as we mentioned earlier, as soon as I hear that we have a normal distribution, I'm going to draw my bell shape, and I'm going to draw these 3 items in. Okay, I'm going to draw my 68% within 1 standard deviation of the mean. And then I'm going to have 2 standard deviations of the mean that I know is going to be 95%. And then 3 standard deviations of the mean, 99.7. All right, so I'm just going to keep this in mind as we talk about any data set that is normally distributed. For example, the distribution of male heights in North America are approximately normally distributed. As soon as I see that, I've got this drawing to go on. If it doesn't supply it, I'm going to make this drawing. With a mean of 70, and if the standard deviation is 4 inches, then 1 standard deviation would be add 4. 2 standard deviations would be to add 4 and 4. 3 standard deviations, add 3 fours. Okay, same direction here, except we're taking off 4. Take off another 4, take off another 4. So I can fill these values in immediately by just knowing the mean and the standard deviation. Then we can answer all kinds of questions about it. So for example, find the height that is 2 standard deviations above the mean. Well, here's the mean right in the middle. 1, 2 standard deviations above the mean. 78 inches is the height of males in North America, 2 standard deviations above the mean. Find the height that is 3 standard deviations below the mean. 1, 2, 3, 58 inches. Right? That's the height that is 3 standard deviations below the mean. If I wanted to find the percentage of men in North America with heights between 66 and 74 inches, between 66 and 74 inches, well, I look here, and that's this, between 66 and 74 inches. Oh, I know that that's 68% of all the males' heights are between 66 and 74 inches. What if we wanted to find the percent of males who have heights between 70 and 74 inches? All right, well, here's 70 to 74 inches. And that, because this shape is symmetric, that's half of my 68%. So 34% of males in North America are between 70 and 74 inches. What if we wanted to know the percent of males that are greater than 78 inches? Well, here's 78 inches. Greater than 78 would be all of these males. Now remember, between (62) and 78, right? That's 95% of the males. So, because the whole population is 100%, the arrow going this way and the arrow going this way must be 5%, right? If 95% is represented by this part in the middle, then the other 5% are the parts on the end. Because it's symmetric, then half of 5% is 2.5%. So notice I can answer all kinds of questions about this population just by knowing that it's normally distributed and what its mean and standard deviation is. Okay. In a normal distribution, a z-score describes how many standard deviations a particular item lies above or below the mean. Thus, the z-score for the data item 78 above is 2, because it's 2 standard deviations above the mean. The z-score can be obtained using the following formula. The data item minus the mean divided by the standard deviation. Data items above the mean have positive z-scores. Data items below the mean have negative z-scores. And the z-score for the mean is 0. So if I'm plugging in my z-scores here, I'd have 1, 2, 3, -1, -2, -3. And at the mean it's 0. If you look at the results of a poll, you will observe that a margin of error is reported. Surveys and opinion polls often give a margin of error. Statisticians use properties of the normal distribution to estimate the probability that a result obtained from a single sample reflects what is truly happening. And here's our little formula. If n is the sample size, there is a 95% probability that it lies within this value of the true population statistic. So this plus or minus 1 over the square root of n times 100% to change it to a percent, excuse me, is called the margin of error. Although the normal distribution is the most important of all distributions in terms of analyzing data, not all data can be approximated by this symmetric distribution with its mean, median, and mode all having the same value. In our discussion of measures of central tendencies, remember that we mentioned that the median rather than the mean is used to summarize income. Below is an illustration of the population distribution of weekly earnings in the United States. There is no upper limit on weekly earnings. The relatively few people with very, very high weekly incomes tends to pull the mean to a greater value than the median. The most frequent income, the mode, occurs towards the low end of the data items. Way more people are on the low end of the income scale than the very, very high multi-billionaires. So the mean, median, and mode do not have the same value. And a normal distribution is not an appropriate model for describing weekly earnings in the U.S. This kind of distribution is called a skewed distribution. A distribution of data is skewed if a large number of data items are piled up at one end or the other, with a tail at the opposite end. If the tail is to the right, it is said to be skewed to the right. So this is a drawing of one that is skewed to the right. If the tail is to the left, it is said to be skewed to the left. So here's one that's skewed to the left. Okay, let's see if we can answer some questions about the normal distribution. The scores on a test are normally distributed with a mean of 100 and a standard deviation of 20. Well, if it's normally distributed, I can draw this bell shape, and I know the mean is 100. If the standard deviation is 20, then if I, subtract 20 and add 20, that's one standard deviation away. If I add another 20 and subtract another 20, that's two standard deviations away. Subtract another 20 and add another 20, I'm 3 standard deviations away. Okay, and I know that this is 68% of the data fall within one standard deviation. 95% fall within 2 standard deviations, and 99.7% fall within 3 standard deviations of the mean. So, if I'm going to find the score that is 3 standard deviations above the mean, 1, 2, 3, 160. Half a standard deviation below the mean, well, that would be halfway between 80 and 100, 90. It's as simple as that. Okay, not everyone pays the same price for the same model of a car. Prices paid for a particular model of a car are normally distributed with a mean of 17,000 and a standard deviation of 500. Well, let's try to draw that. Normally distributed with a mean of 17,000 with the standard deviation is 500, then I'm going to add 500 3 times. 17,500, 18,000, 18,500, and subtract 500 3 times. 16,500, 16,000, and 15,500. And once again, I know that this is 68%. This is 95%. And this is 99.7%. Okay, so if I want to know the percentage of buyers who paid between 17,000 and 17,500, let me put my dot in here for my mean. Okay, well then that's these people right here between 17,000 and 17,500, which is half of my 68%. So 68 divided by 2 is 34%. If I want to know between 16,000 and 17,000, okay, here is 16,000 to 17,000. Well, that's half of my 95%. So 95 divided by 2 is 47.5%. And let's try between 15,500 and 17,000. Well, here's 15,500 and 17,000. That's half of my 99.7. So 99.7 divided by 2, 49.85%. What if we wanted to know less than 16,000? That represents this group, right? Less than 16,000. So if I look from here to here, that's 95%. Right? 95%. So that means this edge and this edge has to be the remaining 5%, but I only have half of it, only one side, so half of 5 is 2.5%. More than 18,500 would be this quantity. But again, if I look, I know from here all the way to here is 99.7%. So this remaining part on this side and this side has to be 0.3%, right? 100% minus 99.7 is 0.3%, but I only have one side of that, so 0.3 divided by 2, right? Half of 0.3 is 0.15%, less than 1%. Okay, what about this? We have a set of data items is normally distributed with a mean of 60 and a standard deviation of 8. Okay, mean of 60 and a standard deviation of 8. So 68, add 8, 76, add 8, 84. Subtract 8, 52. Subtract 8. What's that? 44. And subtract 8, 36. Right? Let me make sure I have the right numbers. 36 plus 8 is 44. Plus 8 is 52, 60, 68. Okay, looks good. Oh, we're converting each data item to a z-score. So that's fine. That's fine. 68. Now I have this, don't forget, I have this formula that says my z-score is my data item minus the mean divided by the standard deviation. So I could plug into that and do 68 minus the mean divided by the standard deviation of 8 and get 8 over 8 or 1. Or I could look over here at my z-score and this is 1, 2, 3, negative 1, negative 2, negative 3. Right? So 68 has a z-score of 1. Okay, 64, I can either plug into my formula, right, and get 64 minus 60 over 8, or 4 over 8 is 1/2, or 0.5. Or I can look over here and see that 64 is halfway between my 0 and my 1 z-score. Okay, 60 is my mean, so my z-score is 0. 48 is right here, halfway between 44 and 52, so it's negative 1.5. Or we could plug into the formula 48 minus 60 over 8 and get negative 12 over 8, negative 1.5. Finding the z-score. Okay, a set of data items is normally distributed with a mean of 400 and a standard deviation of 50. So that means 450, 500, 550, 350, 300, 250. Find the data item in this distribution that corresponds to a z-score of 1.5. So 1.5, right? 1.5 would be right here, halfway between 450 and 500, or 475. Okay. Again, I could plug into this formula up here, except let it equal 1.5, right? 1.5 equals, now I'm looking for my data item, minus the mean over the standard deviation, and I could solve that little equation for D. Or, if I want to know my data item that corresponds to the z-score negative 3, here's negative 3. I already have it calculated on my little drawing. 250. Negative 2.5. Okay, negative 1, negative 2.5 would fall right there, halfway between 250 and 300. So 275. Okay, and finally, using a random sample of 4,000 TV households, Nielsen Media Research found that 60.2%, let me get rid of that right there, found that 60.2% that watched the final episode of MASH. Okay, let's read that again. I got lost in my erasing. Using a random sample of 4,000 TV households, Nielsen Media Research found that 60.2% watched the final episode of MASH. Okay, 62.2% of households. Okay. Find the margin of error in this percent. So again, remember we have a margin of error formula, plus or minus 1 over the square root of n times 100%. Okay, and n is our 4,000 because there were 4,000 households. So all I have to do is put plus or minus 1 over the square root of 4,000, multiply it by 100, and add my percent sign. And of course you don't put the plus or minus in your calculator, right? 1 divided by the square root of 4,000 times 100 gives you 1.58. Let's round to the nearest hundred. It doesn't tell us that, but really we get 1.58113 883 dot dot dot. So if we're going to round to the nearest hundredth of a percent, we would say 1.58% is the margin of error. Now, this says write a statement about the percent of households in the population that tuned into the final episode of MASH. So you want to say something like, we can be 95% confident that between, well, first of all, let's calculate that. So 60.2, so we need to do 60.2 plus 1.58 and 60.2 minus 1.58. right? That's our margin of error. 60.2 plus 1.58, so 61.78. And 58.62. So let's even go ahead and round this, just for sake of an easier sentence, to the nearest tenth of a percent. Now, if we're going to write a statement about the percentage of TV households in the population that turned into the final episode of MASH, what this means is we can be 95% certain, right? We are 95% confident that between 61.8 and 58.6% of households did tune in to that final episode, right? If they found 60.2% watched the final episode, then we're 95% sure that it was actually somewhere between 58.6 and 61.8 that indeed did tune in to watch the final episode of MASH. Okay, I think that does it for this section. I think that does it for the course. If you have any questions, feel free to let me know. I hope you've enjoyed this course. I hope you've learned a lot. Please let me know if you need anything. Good luck.